A giant star is on the brink of exploding, and clinging to its side is a newborn celestial companion that might not survive its embrace. High in the night sky, nestled in the shoulder of Orion, Betelgeuse, a colossal red supergiant, is nearing the final stage of its short but intense life. This final phase marks the onset of core instability, where the star rapidly fuses heavier elements until its core collapses. It's a star so large that if you placed it at the center of our solar system, it would swallow everything up to Jupiter, and it's unstable. One day, not too long from now in astronomical terms, it's expected to erupt in a violent supernova, visible from Earth. But Betelgeuse isn't dying alone. Astronomers have uncovered a hidden partner orbiting dangerously close, a faint, bluish star that hasn't yet matured. This companion isn't just tagging along, it's cutting straight through the outer layers of Betelgeuse's puffed-up atmosphere, disturbing its outer material and likely affecting mass loss and surface turbulence. The interaction turns the region into a glowing, ionized swirl of gas. This is no gentle partnership. It's more like a firefly waltzing through a furnace. The discovery reshapes what we thought we knew about Betelgeuse. For years, scientists were puzzled by its irregular flickers, mysterious patterns of dimming and brightening that defied easy explanation. One particularly strange episode occurred in 2019, when the star's brightness dipped so dramatically that some believed it might explode at any moment. The culprit, it turned out, was a massive cloud of stellar burp, gas and dust spewed from Betelgeuse itself that briefly veiled its surface. But the repeating fluctuations, they hinted at something else, something orbiting nearby. That companion was recently spotted using the ultra-precise imaging power of the Gemini North Telescope in Hawaii. The telescope pierced through Betelgeuse's searing glare and identified the companion, confirming what had long been suspected. Betelgeuse is part of a binary star system. Some astronomers informally call this companion the Beetle Buddy, though its technical nature is still being studied. The two stars make for an odd couple. Betelgeuse is bloated, aged, and on the edge of detonation. Its companion is compact and young. So young, in fact, it hasn't even begun fusing hydrogen in its core, the defining trait of a mature star. It's like watching an elderly titan lumbering toward collapse while a toddler clings to its arm, unaware of the coming doom. Every 5 or 6 years, this smaller star completes a close elliptical orbit around Betelgeuse. And in doing so, it disturbs the supergiant's outer layers, adding heat and energy that may be partly responsible for its erratic brightness. Think of it as stirring a pot that's already boiling over. The implications are huge. This orbiting companion helps explain years of unpredictable behavior. It also provides a rare look at what happens when a massive star lives its final days with a partner locked in a fatal dance. Because make no mistake, this is not a story with a happy ending. The baby star is in mortal danger. 2 possible fates await it. If Betelgeuse goes supernova while the companion is still near, the resulting explosion will likely obliterate it, incinerated or ejected at high velocity into deep space. If instead the red supergiant lives a few more millennia, the companion may spiral inward and be absorbed, vanishing into the belly of its massive host. Either way, the clock is ticking. To appreciate just how dramatic this is, remember, Betelgeuse is around 10 million years old, ancient by human standards, but fairly young for a star. Yet because it's so massive, its life burns out fast. While stars like our sun enjoy stable lifespans of 10 billion years or more, giants like Betelgeuse live fast and die young, their sheer mass accelerating every nuclear process. What will that look like from Earth? When Betelgeuse finally erupts, it will outshine every other star in the sky, possibly even visible in daylight. It won't harm us. It's too far away for that, but it will give humanity front-row seats to a spectacle we haven't seen since SN 1987A or even the Crab Nebula supernova recorded in 1054. And all the while, that quiet little companion continues its doomed loop, threading through the fringes of a star that's tearing itself apart. There's something poetic, even tragic, about their cosmic relationship. One is aging, bloated, unstable. The other is young, barely formed, just beginning to shine, but already marked for destruction. Together, they remind us that the universe is full of unlikely pairs, wild physics, and relentless motion. And sometimes, stars die not alone in the dark, but clasping another in a final fatal orbit.
Stars are beautiful, colorful things. There are red giants. Those are nearing the end of their lives and are on the verge of explosions. Blue stars shine in the belt of the constellation Orion, as well as other places. Yellow ones, like our sun, are pretty ordinary. They're usually warm and stable enough to support life. But look at the night sky attentively. Do you see any green or purple stars? Nope. They're kinda invisible because of the way we humans perceive visible light. The color of a star mostly depends on its surface temperature. The hotter it is, the shorter wavelengths the light it emits will have. The hottest stars are blue or white blue. Those are some of the shortest wavelengths of light. Cooler stars are normally red and red-brown, which are longer wavelengths. At the same time, stars never send out their light in just one wavelength. It's more of a range of light. The wavelengths of light from a star peak in just one color in a bell-shaped curve. But the star emits other colors too. Human eyes have evolved to see yellow and green radiation, probably because our sun emits it mainly in these wavelengths. But a green star emits radiation right in the center of the visible light spectrum, in all possible colors. That's why such stars appear white, which is a combination of all hues. Actually, our sun emits quite a lot of green light, but we perceive it as white. Purple stars, though, are something our eyes won't ever see because they're sensitive to blue light. And since stars emitting purple light send out a lot of blue light too, because these shades are next to each other on the visible light spectrum. The human eye picks up only the blue light. When it comes to other objects in the solar system, many planets seem to have no obvious hue. Look at Venus, Saturn, or Jupiter. They look kinda bland, probably whitish at best, but there are several planets that boast very decisive colors. For example, Mars looks orange-red, Neptune is blue, and Uranus has a beautiful blue-green hue. The planet gets it from all that methane gas in its atmosphere. Meteors sometimes display a vivid green too, and look at breathtaking bright auroras. Green is the most common color of the northern lights. But not stars, never stars. The brightest star in the sky, besides our sun of course, is Sirius. It's twice as bright as its competitor, Canopus, located in the southern constellation Carina. Being the most brilliant, Sirius is very easy to identify. Probably the coolest thing about this star is that it seems to be changing its color. But we'll get to it a bit later. This star is whiter and hotter than the sun. Its surface temperature is 17,300 degrees F, while the sun's surface temperature only reaches 10,000 degrees F. When you combine the immense heat Sirius emits with its girth, 1.75 times the size of the sun, you'll understand why the star looks so bright in the night sky. Sirius has a companion star. It's called the Pup. It's a tiny but incredibly dense white dwarf with a diameter of a mere 7,000 miles. This makes it smaller than Earth. At the same time, its mass reaches 98% of that of the sun. It means that the matter inside this tiny star is squeezed very, very tightly. That's why its gravitational pull is 350,000 times greater than Earth's. A person weighing 150 pounds would weigh 50 million pounds on this star. Now, Sirius is famous for its twinkling, and since it is also the brightest star, we can observe the ever-present turbulence in its atmosphere quite well. As for the star changing its color, it has to do with the atmosphere of our planet. Pockets of air at different temperatures focus starlight this way and that like small lenses. We see it as twinkling. But since white light is made of different colors, one pocket might send some red our way. Another will send blue or yellow in totally random order. That's why it seems that Sirius twinkles in color.
Can a planet be bigger than its parent star? Well, if you mean a star like our sun, it's highly unlikely. But what if it was a white dwarf, the remnant of a star similar to ours that went out after shedding its outer layers and leaving behind nothing but the core? This core is what we call a white dwarf. Usually, it's around the size of our home planet. If a star had a planet bigger than Earth before it extinguished, it's possible that such a planet could survive all the chaos. In this case, a planet that is bigger than its star might actually exist. And we've even found planetary systems like this. But there's one problem. A white dwarf isn't a real star like our sun anymore. It doesn't produce energy, just sits out there getting cooler and cooler. So probably such systems don't count. For comparison, the sun is working non-stop. It is fusing hydrogen into helium in its core. It has been doing it for more than 4 billion years and is going to keep doing it for the next 7 or 8 billion years. The sun is 10 times as wide as the largest planet in our solar system, gas giant Jupiter. And sadly, you can't get a planet much larger than that. If you start adding mass to such a world, it will get smaller, not bigger. So it seems you can find a planet larger than the sun. But there are also dim red dwarf stars. They're the smallest out there, barely massive enough to maintain fusion in their cores. The tiniest stars that we know about have been discovered recently. If astronomers' conclusions are correct, then both of them can hardly fuse hydrogen into helium. And it takes about 0.077 times the sun's mass, or 75 masses of Jupiter, to be able to do that. And still, they're real stars, just very tiny, smaller than Jupiter. One of them is only about the size of Saturn, which must mean that stars can have planets bigger than they are, right? Well, theoretically. When it comes to practice, you can hardly find such planetary systems. We've found and observed quite a lot of exoplanets, which are worlds orbiting other stars. It seems that there are indeed loads of trends out there in space, different masses, sizes, brightness, and so on. But the main trend? Red dwarfs don't usually have gas giants orbiting them. If they do have planets, those are typically small, rocky worlds, more like Earth. Those are also called terrestrial planets. For example, a red dwarf called TRAPPIST-1 has 7 Earth-sized planets orbiting it. But gas giants circling around red dwarfs are extremely rare. Hardly 1 in 100 tiny stars can boast such a planet. This number can be even smaller since the research has been done using candidate planets which haven't been confirmed yet. Plus, the smallest stars are also the dimmest. It means they are extremely hard to detect, and it's incredibly hard to figure out whether they have planets orbiting them, and if they do, whether these planets are gas giants or terrestrial worlds. Still, it's possible that a system where the planet is larger than its parent star exists. But the probability is statistically very low. At the same time, red dwarf stars are very numerous. They're actually the most common kind of star in the galaxy, making up around 70% of all stars. And even though really tiny red dwarfs are relatively rare, there still must be millions or probably even billions of them in the galaxy. And if there's even a small fraction of red dwarfs with gas giants orbiting them, it might still mean that a lot of such systems exist in total, and some of them can have planets bigger than their host star.
Aliens might already be out there, and the next generation of space telescopes could actually see them. Not in flying saucers or shadowy silhouettes against the stars, but in the faint, twisted glow of polarized light bouncing off an alien ocean, or in the ghostly signature of molecules that twist in only one direction, the same quirky habit that all life on Earth shares. And the key to unlocking this interstellar mystery, a telescope so advanced, so precise, it could detect life not by accident, but by design. It's called the Habitable Worlds Observatory, and it's humanity's most serious attempt yet to answer the oldest question: are we alone? At first glance, the HWO might look like just another ambitious piece of NASA's long pipeline of missions, one more telescope among many. But make no mistake, this one is different. It's not built to study galaxies or unravel black holes. Its sole purpose is to find life. Not just planets that could be habitable, but worlds that are inhabited, teeming, thriving, alien ecosystems hundreds of trillions of kilometers away. Getting there, though, is like trying to solve a cosmic crime scene. You can't just zoom in and take a picture of the alien equivalent of a rainforest. You need evidence, layers of it. and the HWO is being designed to collect that evidence with surgical precision. Its mission unfolds in 4 stages, each one peeling back a layer of the unknown. First, identify potentially habitable exoplanets. That alone is no small feat. You're looking for tiny, dim specks of light next to the blinding blaze of their parent stars. But HWO is equipped with a built-in coronagraph, a kind of cosmic sunshade that blocks the overwhelming glare of the star, letting the light from the orbiting planet shine through. Second, look for the hallmarks of life. The most immediate clue? Color. Specifically, biopigments, substances like chlorophyll that reflect and absorb light in particular ways. These signatures show up in polarized light, which vibrates in specific directions. HWO's polarimeter is designed to detect those subtle twists and turns in light, revealing whether a distant world might be cloaked in alien greenery. But even that isn't proof. So the third step is to map the planet's surface. Not in high definition, but enough to distinguish continents from oceans, clouds from deserts, and, just maybe, forests from barren rock. Variations in brightness, reflected light, and spectral fingerprints help sketch out a rough global map. Such mapping, though crude, could be the first time humanity ever sees an alien landscape. And then comes the final, breathtaking step, searching for chirality. Life on Earth exclusively uses molecules that are handed, either left-handed or right-handed, but never both. This asymmetry, called homochirality, is a universal trait of biological systems, and astonishingly, it leaves a telltale signature in circularly polarized light, a kind of light that spirals as it travels. Circular polarization is rare in nature, and its biological origins make it stand out like a flare in the darkness. If HWO detects it, we'll be able to trace the fingerprints of alien life without ever stepping foot on that distant planet. Unlike atmospheric gases that can be formed by volcanoes or other geological activity, chirality is incredibly hard to fake. But here's the real challenge. The signal would be faint. Only about 0.1% of the total spectrum, hidden among noise, distortions, and the glare of nearby stars. But HWO's instruments are being engineered to catch it, to sift the whisper of life from the cosmic static. And it's not alone in the hunt. Telescopes like JWST and upcoming ground-based observatories are already scanning the skies, identifying exoplanets that sit within the so-called habitable zones of their stars, regions where conditions might allow liquid water to exist. These discoveries provide the target list. HWO brings the forensic tools. The mission scope goes beyond mere detection. It also aims to characterize these distant environments in detail. How much of the planet is covered by water or cloud, what kind of atmosphere it has, whether there's seasonal variation. These insights would shape how we think about habitability itself, perhaps even redefining what we consider Earth-like. This isn't sci-fi fantasy. The concept is backed by real hardware plans and international support. The Astro 2020 Decadal Survey prioritized HWO as a flagship mission, recognizing its transformative potential. It's a long-term investment, a decade-spanning project that may define the course of space exploration for the rest of the century. Of course, $10 billion is a towering sum, but so is the cost of Hubble and James Webb, and no one today questions the value of those instruments, which revolutionized our view of the cosmos. HWO could be the next step in that legacy, not just expanding our knowledge, but changing our place in the universe. The implications are staggering. Discovering a planet with biosignatures would change science, religion, philosophy, everything. It would force us to rethink life itself. Are we a fluke or one instance of a cosmic pattern? And what if we find nothing? That answer too is monumental. If life is rare, if Earth is truly exceptional, it places a responsibility on us to preserve what we have, because it may be all there is. One way or another, HWO promises to break new ground. It's not about flashy visuals or viral headlines. It's about deep, deliberate science, about asking the hardest questions and building the tools to answer them. When that glimmer of twisted light finally reaches us, it won't just illuminate a distant planet. It will illuminate ourselves.
Everything around us, as well as all living creatures, consists of atoms. That's what we all learn at school. Atoms come in around 100 types, called chemical elements, and are typically arranged into molecules. We take this fact for granted, but let's say, in the 19th century, the existence of atoms was still hotly debated. And even today, there are some details in this picture that are kind of fuzzy. Some puzzles baffling people a century ago remain unsolved. And Higgs particles have everything to do with this mystery. It's a known fact that the mass of an atom comes mostly from its nucleus. The electrons forming a wide cloud around the nucleus actually make up less than 1,000th of an atom's mass. But an atom's size depends mostly on the electron's mass. If you decrease the mass of the electron, the size of the atom will increase, but it will also become more fragile. At the same time, if you decrease the electron's mass by even a bit more than a factor of 1,000 or so, atoms will get so delicate that even the leftover heat from the Big Bang could destroy them. The mass of the electron, as well as its origin, has puzzled physicists since it was first determined. Photons, particles that make up light, have no mass at all, but atomic nuclei are made of quarks that do have mass. And there's also evidence that neutrinos, those elusive particles streaming from the sun, have tiny masses too. But then, why do electrons, quarks, and neutrinos have mass while photons don't? To explain it, researchers needed fresh ideas, and in the early 1960s, a possible solution was found: the Higgs mechanism. Imagine an unknown field of nature that is not zero and is uniform all over the universe. If this Higgs field could be of the right type, its presence would cause all kinds of particles to develop masses. This field is invisible to us. We can't detect it using our senses, and it's impossible to detect it directly with scientific equipment. Then how can we learn anything about it? You see, the Higgs field is like air. When you disturb either of them, they vibrate, producing waves. In the case of air, you can create such waves quite easily. Just shout or clap your hands. Your ear will detect the waves in the form of sound. But in the case of the Higgs field, it's extremely difficult to create the waves and even trickier to observe them. To make them, you need a giant particle accelerator, and we have one. The Large Hadron Collider located at the CERN laboratory outside Geneva, Switzerland. As for detecting them, you need special building-sized scientific instruments. Luckily, those are available too. So how can you do it? Smashing two very energetic protons together can create incredibly quiet Higgs waves. Plus, 1 in every 10 billion collisions can do it. The wave that is created is the quietest possible wave in the Higgs field. It's called a Higgs particle or Higgs boson. Producing a Higgs particle is actually the easiest part of the process. Detecting a Higgs particle is the hard part. While a sound wave always travels freely through the air, a Higgs particle disintegrates into other particles in less time than light needs to travel through an atom. All that the scientific instruments can do is measure the debris from the exploding Higgs particle as precisely as possible. After that, they can try to work backward and determine whether a Higgs particle could have been the source of that debris. But it's not enough to create just one Higgs particle, since its debris isn't distinctive enough. A collision of two protons might create debris similar to what might emerge from a fragmenting Higgs particle. Then, how can we determine that exactly Higgs particles have been formed? The key here is that even though Higgs particles are rare, their debris is relatively regular in appearance. It helps researchers pick out the typical ringing of the Higgs field amid the cacophony created by other similar-looking processes. Carrying this out is an incredibly hard and complex process, but somehow humanity has managed to do it. And even though this discovery doesn't mean the end to the puzzle about the masses of the known particles, it gives us hope that we will eventually solve it.
Asteroid strikes, gamma-ray bursts, supernovae blasts, and other terrifying threats could potentially take out humanity. but one of them is inescapable, a cataclysmic event that will happen around 1 billion years from now and most likely rob our planet of its oxygen, effectively wiping out all life forms. Nearly 2.5 billion years ago, there was a period called the Great Oxidation Event. It gave us a breathable atmosphere, thanks to which we're all alive today. Cyanobacteria, also known as blue-green algae, appeared on Earth, filling the atmosphere with oxygen. It eventually led to the appearance of a world filled with multicellular life forms. But then, one of Earth's greatest die-offs occurred. It happened 450 million years ago. This event is known as the Late Ordovician Mass Extinction. Scientists think it might have happened because the inverse process took place. The level of oxygen on the planet dropped dramatically, and it lasted for several millions of years. It's unclear what could have caused such an extreme event. During this period, the continents formed one jumbled mass called Gondwana. Most life on Earth lived in the oceans, but plants were starting to colonize land. Near the end of the Ordovician period, a climate shift covered the supercontinent with glaciers. This dramatic cooling alone was enough to lead a lot of species to the brink of extinction. And then, oxygen levels plummeted, which caused the second wave of extinction. Scientists have found evidence of this event in seafloor samples gathered from all over the world. Some are sure that glaciers were responsible for changing the layers of the oceans, which had previously had unique temperatures and specific concentrations of elements like oxygen. However, the exact cause of the oxygen drop is still unclear. Whatever the cause, more than 80% of life on Earth disappeared during the late Ordovician mass extinction. Could a deoxygenation event happen again? Some researchers draw an eerie comparison to today's situation. They say that climate change is already reducing oxygen levels in our oceans. It's likely to make loads of species go extinct and the world to change beyond recognition. Now, even if global cooling triggered the late Ordovician mass extinction, what sparked this process in the first place? There's a theory claiming it could have been a gamma-ray burst. These bursts seem to be the most violent and energetic explosions in space, and they might be related to supernovae. Thankfully, we haven't seen such a burst close enough to fully figure out what it is. So far, they have only been spotted in other galaxies. If a gamma-ray burst occurred in our home Milky Way galaxy, it could also lead to a mass extinction on Earth. A burst pointed in our direction might only last 10 seconds or so. And still, it would destroy at least 50% of Earth's ozone layer. Yes, in such a short period of time. Even a relatively small amount of ozone depletion is enough to cause serious harm to our planet's natural sunscreen. And wiping out ozone on a large scale can wreak havoc, finishing huge numbers of species, starting with the ones living in the upper levels of the ocean. Gamma rays also break apart atmospheric oxygen and nitrogen. These gases turn into nitrogen dioxide, commonly known as smog. If this smog blanketed Earth, it would block out sunshine and trigger a global ice age. But our ultimate fate is much more dramatic than any of these scenarios. Most life on Earth will eventually disappear due to lack of oxygen after solar activity causes atmospheric oxygen to drop back down to the level it had been before the Great Oxidation Event occurred. The sun ages and puts out more and more energy. At one point, around 1 billion years from now, Earth will reach the point where atmospheric carbon dioxide will begin to break down. That's when oxygen-producing plants and organisms will disappear. Earth won't have enough life forms to sustain the oxygen-rich atmosphere all living beings on our planet need. This process may take as few as 10,000 years, and it seems to be unavoidable. Luckily, we still have around 1 billion years to figure out how to save ourselves.
If the universe is everything, then there is nothing external for it to expand into. But we know for sure that it does expand. So the question is, what exactly is it expanding into? According to the theory of cosmic inflation, the universe was once filled with large amounts of energy. It was similar to hypothetical dark energy, but much greater in magnitude. It made the universe expand faster and faster. As a result, the universe was getting colder and emptier. And then, after growing this way for a very long, possibly infinite amount of time, most of this energy got converted into matter and radiation, which triggered the Big Bang. The Big Bang was the moment when the whole universe was squeezed into a tiny, super hot, and extremely dense ball we call a singularity. And all of a sudden, when it was less than 1 second old, this tiny ball started to unpack at speeds we can't even imagine. It was so hot that particles were moving extremely fast, crashing into one another and creating pairs with their opposites, like matter and antimatter. When the universe was 1/100th of a billionth of a trillionth of a trillionth of a second in age, it experienced an incredible burst of expansion that we know as inflation. At that moment, the universe doubled in size at the speed of light. And after that, it doubled in size at least 90 more times, growing from a subatomic-sized formation to a Gulf-sized structure almost instantly. After this burst of inflation, according to NASA, the growth of the universe continued, but it slowed down. As the universe kept expanding, it started to cool down, and matter formed. 1 second after the Big Bang, and the universe was already filled with neutrons, protons, electrons, anti-electrons, photons, and neutrinos. If we somehow managed to observe the universe when it was just a trillionth of a second old, we'd see that it was the size of Earth's orbit around the Sun. When the universe was a mere 1 second old, it was too hot for nuclear fusion to occur. At that time, its radius was just 10 light years, which is enough to enclose the 9 nearest star systems we know about. When the universe was 1 year old, it was smaller than our home galaxy and unbelievably hot. Finally hot enough to start nuclear fusion. When the universe was 3 years old, it was roughly the size of the Milky Way galaxy. When matter started to dominate radiation, which happened when the universe was around 10,000 years old, the size of the universe was about 10 million light years. It would be easy to think of the Big Bang and the resulting expanding universe as an ordinary explosion, where everything is expanding from a central point. But it's not a good analogy. There's a better one. Look at the surface of an inflating balloon. It'll be a 2-dimensional equivalent of our 3-dimensional universe. The balloon fabric will be space. These dots marked on its surface will represent galaxies. You see, they're moving apart as the balloon expands, but it happens only because the fabric, representing space itself, is expanding. The galaxies aren't moving on their own, and there's no central point for the expansion. The balloon is expanding into the 3rd dimension, and that's where the analogy is getting trickier. Does it mean that our universe is expanding into some higher dimension? If there's no larger multiverse and our universe is all there is, then there's nothing outside of it. Not even a vacuum, which is still part of space. It means there's no point in asking what the universe expands into. If there was a 2-dimensional being on the surface of our expanding balloon, they would be able to observe all distances in its surface 2D world getting larger. But they wouldn't see the 3rd dimension into which the balloon is expanding. The same goes for us, 3-dimensional creatures. We see the distances between galaxies growing, meaning the inflation of space, but we can't perceive additional space dimensions into which the expansion is moving beyond our 3. Even if space is indeed expanding into some higher dimension, our current knowledge of physics doesn't allow us to find out anything about it. It's likely to be beyond our comprehension.
Imagine you're looking up at the sky on a clear night, and you see all those beautiful stars twinkling up there. Well, one of them is Betelgeuse, a celebrity among stars. If you want to catch a glimpse of it, look up at the Orion constellation. It low-key looks like an archer holding a bow, and you can spot Betelgeuse as the reddish-orange dot on their shoulder. It's one of the brightest stars in the sky, so it's hard to miss. Betelgeuse is not your ordinary star. First of all, it's gigantic, up to 1,000 times the size of our sun. Can you imagine that? It's so enormous that if we could somehow replace our sun with Betelgeuse, it would engulf all the inner planets, including Earth. And here's another fun fact. When we look at Betelgeuse, we're actually looking back in time.
Yep, you heard it right.
Betelgeuse is about 600 light years away from us, so the light we see today actually left the star 600 years ago. It has quite a history. This star has been shining brightly for millions of years. Long, long ago, even before smartphones and telescopes, ancient Sumerians were the first to spot Betelgeuse in the sky, and it's been a diva this entire time. For example, in 1866, Betelgeuse became one of the brightest stars in the night sky. It was so dazzling that people could see it even during the day. Astronomers all around the world went bananas documenting this extraordinary event. Since then, Betelgeuse has been playing hide and seek with us. It all started when Betelgeuse started to dim back in 2019. Since then, it likes to dim and brighten sporadically. But these changes in brightness tell us about something important. As we mentioned, Betelgeuse was always a bit of a troublemaker. It's been living a fast and furious life. Because of that, it has been burning its fuel at an incredibly fast rate. The changes in the star's brightness are clues that Betelgeuse is approaching the end of its life cycle. The drama intensified when the Hubble Space Telescope snapped jaw-dropping images of Betelgeuse, like it was getting ready to blow its top. All this made scientists think that the star is close to retiring in a dramatic way. It's about to go supernova. So picture a star partying hard, powered by the fusion of hydrogen atoms. It's like the star's own energy drink, but just like any party, the fuel starts to run out. That's when things get interesting. As the star guzzles up its hydrogen fuel, it slowly begins to run on empty. It can't sustain itself anymore. So now, it's time for the grand finale. This finale is called supernova. The star collapses in on itself like a deflating balloon. The pressure and temperature inside skyrocket to mind-boggling levels, and this celestial tantrum triggers a colossal bang. So you can see why observing Betelgeuse is like having a front-row seat to the spectacular drama. But here's the big question. When will this happen? Well, the answer is not as simple as setting a timer. You see, stars have their own schedules, and Betelgeuse is no different. It could be tomorrow, or it could be thousands of years from now. Scientists have come up with only a rough estimate. They believe that Betelgeuse will go supernova within the next 100,000 years. Quite a spread, huh? Sure, that sounds like forever to us, tiny humans. But in the vastness of the universe, it's just a blink of an eye. But there's a chance, just a tiny chance, that Betelgeuse could surprise us all and go supernova much sooner. Considering its dips in brightness, we might be in for a show within the next few hundred years. We'll just have to wait and see. Now, if Betelgeuse does go kaboom, what will happen? Well, get ready for a show like no other, folks. When a star collapses under its own weight, it unleashes a cosmic firework of epic proportions. The star releases a crazy amount of energy in the form of light and heat. Betelgeuse's supernova is going to be extra special. It's like the superstar of supernovas. It will shine so brightly that it might even outshine the other stars in the sky. Picture that, Betelgeuse stealing the spotlight. The show could be so bright that you won't need a telescope to catch a glimpse. Nope, you'll be able to see it with a naked eye. It might even be visible during the day, making the sky look like it's hosting the coolest rave ever. After that, the supernova will keep us entertained for weeks. It will be like having a second moon in the sky, shining as bright as the full thing. Imagine that, 2 moons dancing together in the night. After several weeks of lighting up the night sky, Betelgeuse's supernova will slowly fade away, but it would leave behind a souvenir, an ethereal remnant. It's like a fading memory of the star's epic performance. This remnant, too, would slowly fade away over the course of several months. But it's not just about the light show. The boom will send out powerful shockwaves, and we might actually feel them right here on Earth. It's like the universe giving us a gentle tap on the shoulder, saying, hey, look at this amazing spectacle. How dangerous will it be for us? Well, we know that Betelgeuse's supernova would send dust and gas shooting into the atmosphere. It's like a big space sneeze. And this sneeze could cause a decrease in global temperatures. We're talking serious climate impact here. It could even lead to a mini ice age. But these are just assumptions. We don't know for sure if the consequences will really be that serious. But, of course, we want to be prepared for this event just in case. That's why scientists are studying Betelgeuse closely. But, in addition to serious scientific research, astronomers also have a blast of celestial comedy. Jokes are flying left and right. Someone has even created a Betelgeuse status account, which you can check yourself. So, as you can see, the star is keeping us on our toes. Astronomers keep observing it, and they need our help too. They want us to keep an eye on Betelgeuse and report any changes we see. How do you do that? First off, channel your inner astronomer and observe Betelgeuse. Take a peek at the star and note down what you see. Is it twinkling, shining, or feeling a bit dim? Jot it all down. Then be a superstar yourself and report your observations to the astronomers. Your observations will help them track Betelgeuse's journey towards its big supernova moment. You can also join in on some citizen science projects. They're super fun and easy, trust me. One cool project you can jump into is the Betelgeuse brightness monitor. By participating, you help scientists keep tabs on how bright Betelgeuse is shining. Your contribution can make a real difference. So join the monitoring team. You'll be part of something amazing, and who knows, your observations might even help predict when Betelgeuse will show off its supernova magic. By doing that, we can assist them in monitoring this superstar and learn more about the fascinating world of stars. But that's how we can help scientists to predict this event. Now, how can you personally prepare for it? First things first, you'll need the right gear to catch all the supernova action. A trusty telescope is like your front row ticket to the starry show. It'll bring you up close and personal with Betelgeuse's performance. And remember, you'll need special eyewear to shield your eyes from the intense burst of light. Safety first. And of course, prepare in case it decides to mess with our climate. Stock up on essentials, like warm clothes and supplies, just in case we experience a mini ice age. But let's just hope it won't happen. So keep your eyes on the night sky, my friends. Betelgeuse may not be ready to blow up just yet, but when it does, it will be a sight to behold. Until then, let's enjoy the twinkling stars. And remember, there's always something extraordinary happening in the vastness of space.
Now see here, astronomers have recently discovered a neutron star, also known as a dead star, spinning at an extraordinary speed of 716 times per second. It makes it one of the fastest spinning stars we've ever found in the universe. And it's not just about its speed. The surface of this neutron star is erupting with super powerful explosions almost non-stop. But before we dig deeper into the mystery of this neutron star, let's figure out what these stars really are. They form from the remnants of massive stars that are at least 8 times the mass of the Sun. When such stars exhaust their nuclear fuel, they can no longer counteract the force of gravity pulling their matter inward. This leads to the collapse of their cores, triggering a massive supernova explosion that blows away the outer layers of the star. What's left behind is an ultra-dense core. That's a neutron star. These stellar remnants are incredibly small, typically just 12 miles wide. At the same time, they pack in more mass than the Sun. The density of neutron stars is also overwhelming. Imagine taking the mass of 2 suns and squeezing it into a sphere about the size of a city. A single teaspoon of neutron star material would weigh around 10 million tons. That's the same as the combined weight of 85,000 blue whales. Such an extraordinary density is what gives neutron stars their immensely powerful gravitational fields. When matter falls onto a neutron star, it accelerates to speeds of millions of miles per hour before slamming into the surface. The energy release from such impacts is truly astonishing. Now, despite its name, inside a neutron star, there are not only neutrons. A few protons survive down there too. Now, normally, protons repel each other since they have the same positive charge. But in a neutron star, that crushing gravity forces them so close together that the strong nuclear force takes over. It pulls them toward the neutrons like they're all part of the same team. Inside the star, things get stranger the deeper you go. Near the surface, neutrons clump into blobs, kind of like a neutron gnagi. A bit further down, these blobs link together into long chains, forming what scientists call the spaghetti layer. I'm getting hungry. At even greater pressures, the spaghetti chains fuse side by side, creating flat sheets. Think neutron lasagna. Keep going any deeper, and the lasagna eventually breaks down into a uniform mass. But even then, the structure isn't smooth. There are gaps, long tube-shaped voids that look a lot like penny pasta. So inside a neutron star, you've got layers of gnocchi, spaghetti, lasagna, and penny pasta. And each of them represents the mind-bending results of physics under insane pressure. Okay, I'm definitely having Italian for lunch today. Now, the recently discovered neutron star is part of a binary system located in a dense star cluster. This cluster is situated near the center of the Milky Way galaxy, approximately 26,000 light-years from Earth, in the direction of the Sagittarius constellation. The record-breaking spin of the star is extraordinary. If we take a period of not a second, but a minute, it'll be over 42,000 revolutions per minute. At the same time, the newbie ties with another neutron star, which spins at the exact same speed. Such extreme rotation rates are rare and make these stars cosmic outliers in terms of behavior and properties. Oh wait, we can't but mention our neutron star's binary partner. It's a white dwarf, a dense remnant of a star similar in size to our Sun. This white dwarf is pretty fast too. It orbits the neutron star once every 11 minutes. This makes the couple a binary system, with the shortest orbital period ever observed. Imagine a stellar object zipping around its partner faster than the time it takes to prepare a cup of coffee. Yep, that's the kind of speed we're talking about here. This tight, rapid orbit shows how powerful gravitational forces are inside the system. So, you might be wondering what makes neutron stars spin so rapidly. It's something called the conservation of angular momentum. Let me explain. When a massive star collapses into a neutron star, it shrinks dramatically. Such a rapid compression gives an instant boost to its spin. It's like an ice skater spinning faster when they pull their arms inward. And the smaller the star gets, the faster it spins, which results in extreme rotation rates. In binary systems like this one, neutron stars can achieve even faster spin rates. Their trick is to steal matter from their companion stars. This process is called theft. No, accretion. The stolen matter carries that very angular momentum, which adds to the neutron star's rotation speed. The accreted material can also build up on the neutron star's surface, eventually. It triggers powerful thermonuclear explosions. They release immense amounts of energy, temporarily making the neutron star shine up to 100,000 times brighter than our Sun. It allows astronomers to study the intricate details of these extreme environments. NASA's X-ray instrument on board the International Space Station, officially called the Neutron Star Interior Composition Explorer and thankfully nicknamed NICER, observed 15 thermonuclear explosions on the surface of our neutron star between 2017 and 2021. One of those bursts displayed a unique pattern called thermonuclear burst oscillations. Those are highly asymmetric patches of brightness on the burning surface layers of accreting neutron stars. This pattern matched the spin rate of the neutron star and thus confirmed its extreme rotational speed. But wait, the best part is coming. While neutron stars are already extreme, there's another class of them that takes things to a whole new level – magnetars. Now, magnetars are neutron stars with unimaginably strong magnetic fields, up to 1,000 trillion times stronger than Earth's magnetic field. These fields set them apart from other neutron stars. They can distort atoms in nearby objects, making life impossible anywhere near them. As for the energy density of a magnetar's magnetic field, it's so high that it's 10,000 times greater than the mass density of lead. Magnetars also produce bursts of X-rays and gamma rays that are so powerful they can temporarily outshine entire galaxies. These bursts are often triggered by star quakes, violent shifts in the magnetar's crust caused by their own magnetic fields. For example, a gamma-ray burst from a magnetar in 2004 was so strong that it disrupted Earth's ionosphere. It hit Earth, and it was so intense that several satellites picked it up. The SWIFT satellite, built specifically to detect gamma-ray bursts from across the universe, didn't just detect the blast, it got hit with so much energy that its sensors got completely overloaded. And SWIFT wasn't even facing the burst. The energy was so strong it passed through the spacecraft and still overwhelmed its cameras. If a magnetar was located as close to Earth as the Moon, its magnetic field would erase all credit card data on the planet by wiping the magnetic stripes clean. Whoa, that's the level of power we're dealing with here. Magnetars are extremely active, but for a relatively short time. Their intense magnetic fields decay after about 10,000 years. After that, they stop emitting strong X-rays and gamma rays. Astronomers think that there are at least 30 million inactive magnetars in the Milky Way galaxy alone. These silent cosmic relics are scattered all over the galaxy. Neutron stars and magnetars serve as laboratories for extreme physics. They allow astronomers to have insights into the behavior of certain matter under conditions you can never replicate on Earth. The incredible density of these objects helps scientists figure out what happens when protons and electrons get compressed together to form neutrons. This creates states of matter that don't exist anywhere else in the universe. These violent explosions on neutron stars and magnetars also play a critical role in the formation of heavy elements like gold and platinum. These elements get scattered all over the universe during these energetic events, eventually becoming parts of planets and stars and you and me. Oh, by the way, NASA's NICER instrument has played the key role in uncovering the mysteries of neutron stars. Its ability to detect X-rays with high precision allowed astronomers to study the rapid spin of the neutron star we've been talking about and the thermonuclear bursts that occur on its surface. So, what could be nicer than that? Now, scientists have a wild theory. What if our entire universe is actually inside a black hole? This is called the black hole cosmology. Some scientists have the idea that our observable universe and everything we see around us might be tucked inside a black hole, which exists inside another parent universe or even multiverse. And then this multiverse could be part of a bigger one, and so on, kind of like a stacking doll. Sounds like pure science fiction, but this is based on some curious facts. When scientists create the timeline of our world, they say that everything started from a singularity. If you kept squeezing a giant ball smaller and smaller, at some point it would get super dense before it crushed. Well, it's hard to imagine, but in space, it's possible to squeeze a crazy amount of mass into a teeny tiny point. This point is called a singularity. The matter gets crushed into an infinitely small space, less than an atom, and it holds all the same mass of everything, while taking basically no volume. Inside this singularity point, things get so intense that the normal rules of physics just stop working. Everything we know, time, space, matter, breaks down and can't be applied anymore. Basically, what happens from now on is beyond our understanding. So, scientists say that this was the starting point of our world. When the Big Bang happened, it's like this tiny dot with everything inside it expanded to everywhere. This started forming the universe as we know it. And here's the thing. Scientists assume that singularity also exists deep within black holes. General relativity says that a black hole is born when something really big, like a huge star, collapses under its own weight. Gravity gets stronger the bigger the mass is. With a mass of a huge star, tens of times bigger than our Sun, this tiny point would have an unbelievable gravity. It's why it starts sucking in all the stuff around it and curves the fabric of space-time so much it looks like a hole in space. And this would be the center of a black hole. It's a dot where all these things fall into and get crushed into an infinitely dense point. So, could our universe itself be just a little singularity dot inside a huge black hole inside of another universe? Well, that would be wild. So, it's not that easy to compress something so much that it literally warps space-time. You'd need to squeeze it like crazy. If you wanted to make a small black hole, like a human size, you'd need to shrink them down to the size of an atomic nucleus. If you want a black hole the size of a chickpea, you'd have to compress our entire planet to that. But our universe is 99% empty space. There are trillions of miles of just nothingness between the stars. If you were to pack all the matter in the universe together, the result would be surprisingly small. Everything around us, including galaxies, stars, planets, and dust, would only fill about 1 billion cubic light years. It would be a cube about 1,000 light years on each side. For comparison, our Milky Way alone is 100,000 light-years in size. That's how sparse the universe is. But at this density, it would also be very, very massive. The resulting mass would likely collapse into a black hole. And here's the wildest part. The resulting black hole would be roughly the same size as the universe itself. It would also have the same mass and energy, as well as the same average density. The size, or radius, of the black hole grows together with its mass. The more stuff it eats, the bigger it is. But the density works the other way around. The black hole gets less dense as it grows. For a size that big of our entire world, it would be pretty sparse as well. And it's not the only coincidence. We have this thing called the Hubble radius, also known as the cosmological event horizon. If we imagine our observable universe as a giant bubble, then think of its edge like the farthest part of the universe we can see. When you stand in a field and look around, trying to see as far as you can, your eyes will draw a circle. This is like that. There might be more beyond that point, but we'll never know. Beyond this horizon, the light from distant parts of the universe will never reach us. That's because light travels at a certain speed, and the space between us and those regions is expanding too quickly. It's like running towards something while super strong winds try to blow you away. Until we stay on Earth, we're cut off from those far-off corners forever. The black holes have something eerily similar called an event horizon, or the Schwarzschild radius. This is the point of no return. This is the imaginary line that's often depicted as a light contour around the black holes. Anything crossing an event horizon, falling inside, is lost forever. No light, no matter, no information can escape from there. Black holes' gravity is way too strong, so they're perfect space vacuum cleaners. And as we mentioned before, if we create a black hole the size of the universe, they would have the same mass and the same event horizon radius. Now, while some scientists think this could just be random coincidences, others believe it's a clue that our universe might actually be inside a black hole. The theory also suggests that our universe might not be the only one. It could exist in one of many black holes scattered throughout a large multiverse. In this crazy model, each one of them, both in our world and our parent world, could lead to its own universe, with its own set of physical laws and structures. Now that would be some weird chain. There's this theory that says that universes could be born inside of black holes, sort of. It's called the Einstein-Cartan theory. This idea talks about singularity as well, but in a different way. It says that instead of collapsing into an infinitely dense dot, the matter might create a wormhole. This is like a tunnel through space and time. This wormhole, also known as an Einstein-Rosen bridge, could connect two different places of our universe. In that case, one side of the tunnel is the black hole, and on the other side, there would be a whole new universe forming. So it could work like a teleport. As soon as you pass the event horizon, you travel to the new world. But in that case, there should be an exit. Some scientists made it up and called it a white hole. It doesn't literally exist, not as far as we know, but it could be possible somewhere on the other side. It would serve as an exit of a wormhole, an area where matter is always ejected instead of pulled in. So it's like you can't throw anything in there, it would get expelled immediately. That's all purely hypothetical, of course. All this stuff fits well into the concept of the Big Bounce. This idea says that instead of our universe beginning with a singular Big Bang, it bounced from a previous state of collapse. Remember the squeezed ball analogy? Well, maybe there used to be another universe ball that got super compressed to a minimum size before rebounding and expanding again. So instead of a universe born from nothing, we might live in one that's a cosmic recycling of another. There's also another version of this theory, sometimes called shockwave cosmology. The idea says that the Big Bang could have been caused by a boom inside a black hole, and this could create the expanding universe we see today. As the universe expands and the matter density decreases, the black hole would eventually transform into a white hole, the reverse of a black hole, where matter is expelled instead of pulled in. But even though we have all these interesting connections, they're not evidence. There are no experiments or observations that could prove or disprove these wild theories. So they all remain speculation for now. But at least it's fun to speculate.